Hello, Professor. This is Zhongyin Ye, and this is my presentation of normalization. And first of all, I want to clarify the definition of normalization. Database normalization is the process of structuring a relational database in accordance with the normal forms to reduce the data redundancies and improve data integrity, and which entails organizing the columns and tables of the database to ensure that their dependencies are properly enforced by database integrity constraints. So in my understanding, or in short, I think the normalization is a regulation that when you need to create a database that you should follow so you can improve the efficiencies of your database. So what are the first normal form and second and also third NF and BCNF? I create a graph to illustrate its process. It's actually a sequential process. So if you want to verify if this database qualifies for first NF, then we need to make sure that its value in each column must be atomic. Then after it qualifies for the first NF, we need to check if it has a single primary key. If it's yes, then it automatically qualifies for second NF. If it is no, it has multiple primary key, then we should check non-primary keys are fully dependent on the primary key. And after qualifying for second NF, then we should check that if the non-primary keys have no dependency, which means we want to make sure that there is no dependencies between any two of the non-primary key. And after we make sure that there is no dependencies within any two of non-primary key that is qualified for third NF, then we can check if there is any dependencies between the primary keys. If the primary keys have no between dependencies, then we say it's qualified for BCNF. Okay. So besides from the first, second, third NF, there's actually also have 4, 5, and 6 NF. And it's also a sequential process. After we make sure it qualifies for third NF, then we can check if it has the multi-value dependencies. If it has no multi-value dependencies, we can say that it qualifies for 4NF. And then we check about if this table or data cannot have lossless decomposition into any smaller table. If the answer is yes, that is qualified for 5th NF. And then the final part is that after it qualifies for the 5th NF, we could check that if every relationship consists of a candidate key plus no more than one other attribute. And if if you qualify for this condition, then you qualify for the 6th NF. So it sounds like a very complicated sequential process of the normalization. So why do we bother or need to do the normalizations? And what happens if we do not do it? So first of all, the advantage of doing it is because it can increase the consistency of data. The information is stored in one place and one place only, so it can reduce the possibility of inconsistent data. And it's easier object-to-data mapping. The highly normalized data schemas in general are closer conceptually to object-oriented schemas, because the object-oriented goals of promoting high cohesion and loose coupling between classes result in similar solutions, or at least from a data point of view. So what happens if we don't perform the normalization? It may have the anomalies in 3 kind of conditions: operation, when you insert the data, update the data, or delete the data. So it seems like perform the normalization is really good. So here is the question: that's if should we perform the the normalization on every data set that we have? The answer is negative, is no. Because for some specific kind of data, the data which is static, it doesn't benefit from normalization, because the normalizations will make the whole database architecture more complicated. So it's not always normalization is not always better for some specific data set. So here come what are the drawbacks of performing normalizations. As I mentioned before, it's not always good to perform the normalization. Here are the drawbacks. First of all, it might spread out the data into more tables, and which results in the need to join tables increases, and the text becomes more tedious. The database becomes harder to realize as well. And when we design an algorithm to find specific values in the table, you may find after the normalizations, the algorithm's efficiency, time complexity will increase because the architecture within the data sets is more complicated, and there are more tables inside the database. So searching data's efficiencies will definitely decrease. Okay, so what are the three anomalies if we don't perform the normalization? There are three kinds of anomalies may occur. The first of all is update anomaly. The data's inconsistency that results from data redundancies and partial update. For example, a student group is defined, so that new values are not allowed. So if a new employee is hired but not immediately assigned to a student group, then this employee could not be entered into the database. This results in database inconsistencies due to omissions. And the second is insertion anomalies, inability to add data to the database due to absence of other data. For example, if a system is designed to require that a customer be on file before a sale can be made to that customer, but you cannot add a customer until they have bought something. So you can see the problem here. This is the problem we call the insert anomaly. And for the third deletion is deletion anomalies. It happens when the deletions of unwanted information cause desired information to be deleted as well. For example, if a single database records contains information about a particular product along with information about a salesperson of one company, and after the salesperson quit, the company remove the data of salesperson, and the information about the product he sold is deleted as well. That's not the condition that we'd like to see, and we call this condition the deletions anomalies. So here comes another terminology, is determinants. What are determinants? A determinant in a database table is an attribute that can be used to determine the value assigned to other attribute in the same row. By this definition, any primary key or candidate key is a determinant, but there may be determinants that they are not primary or candidate keys. You can see the table below. For the employee ID, every employee ID is unique. So if we look up to the employee ID 123, you can easily get the return value of first name, last name, date of birth. It's Megan Brown. So we can call employee ID as a determinant, and also we can set it as a primary key. But a primary key or a candidate key is a determinant, but the vice versa, there is no vice versa. When data is a determinant doesn't mean it is ensured to be the primary key or candidate key. So this problem is what are the functional dependencies? The functional dependencies, the information stored in a table can uniquely determine another information in the same table, then it's called functional dependencies. And there are three types of functional dependency. First is following. An attribute is fully functional dependent on another attribute. If it is functionally dependent on the attribute and not on any of its proper subset. And for transitive, when an indirect direct relationship called functional dependency is called transitive dependencies. For example, if attribute P has functional dependencies with attribute Q, and attribute Q have functional dependencies with attribute W. If we put these three attributes together, P, Q, W, we can see there is actually a transitive dependencies between attribute P and attribute W. And the last one is the partial dependencies. Partial dependencies occurs when a non-primary attribute is functionally dependent on part of a candidate key. Okay. So let's read some example of the normalization to better understanding the concept. First of all, before the normalization, the first step is that we should check that every column should have a single value. Like you can see the table on the top. In the contact column, there is actually email and phone information inside. So based on first normal form's definition, we have to split the contact column into email column and phone column, so it can be qualified for first NF. Okay, so the second NF, again, we can see the table on the top. The primary keys are starting numbers and class number, and all the other attributes are name, sex, email, phone, and class address. And suddenly we found that class address is partial depending on the class number only. It does not depending on starting number. So we should separate them into the two table below to make it qualify for the second NF. So next is the third NF. In the top of the table, in this case, we can see the primary key is the starting number, and the other attributes are name, sex, email, phone, bonus label, and bonus. The bonus label and bonus are both non-primary key, but they have dependencies between them. So we have to make it into two tables to make sure that the bonus label go to another table and qualify for third NF. And the final example is the CNF. In this case, you can see the table on the top. The two primary key is storehouse ID and manager ID, and other attributes are goods ID and goods number. And if we only look at the primary key, we can find that actually the storehouse ID has dependencies with manager ID. So we have to separate them into two tables to qualify for BCNF. So that's all for my example, and here's some questions for the class and also some reference. That's all of my presentation of normalization. Thank you for your listening.